Welcome back to algebraic graph theory seminar, everyone. Today, Pierre and Antoine back now will tell us about the bivariate P-polynomial association schemas on the fibers of a uniform poset. Go ahead.
Thank you. Thank you for being here. Thank you for the invitation to give this talk. So today I'll talk about bivariate and multivariate generalization of association schemes. And by the end, we should talk about this structure of fibers on uniform poset. And this is all based on work, past work and ongoing work with very nice people, Nicolas Crampé, Loïc Poulain-Dancy, my supervisor, Vinet, Mary Zaimi, and the actual host, Xiaong. And yeah. So for this talk, I want to start with some motivation on why one should care about these multivariate generalization of well-known and beloved special functions. Then we'll discuss about the actual definition of multivariate P-polynomial association schemes, their interpretation in terms of graphs, and by the end, their relation with uniform posets. Okay. So because I'm doing physics most days, the motivation will be a bit of will have some physics flavor. So what I'm asking you to consider is, imagine that you're a physicist, a quantum physicist in a lab, and you're considering a particle confined in a normonic potential, and you want to do some measurement on this particle, and you need to do measurement with different angles. You know, you're going to move your instrument around. And so you need to be able to relate the measurement you do with one orientation of your instrument with another orientation. So how do you do that in quantum mechanics? Well, we can formalize a bit the question. The Hamiltonian of the particle in this setting is given by the operator on the top. So it's basically a Laplacian plus a term, which is the quadratic potential. And if you're interested in the energies of the system and the stationary state, you need to diagonalize this Hamiltonian, find the solve the eigen problem for this operator. And if you do it by solving by doing separation of variable in Cartesian coordinate, so finding the eigenfunction of h using this technique, you find that the wave function that satisfy this equation are a product of three Hermite polynomials. So even if we start with a potential, which is a mirror symmetric potential, the basis of wave function for the stationary state that we find are not invariant under this rotation, right? Because if I do a rotation that mix x and y, it is a bit obvious that in this product of three Hermite polynomial, it will not be left invariant under this mixing of the coordinate. And so if I do this construction after or before having done this rotation, I will find two different bases for the stationary state of the system. And so if I want to relate the measurement I do in one basis and the measurement I do in another basis, I need to be able to compute what is the scalar product or the overlap between the vectors in these two bases, between these two wave functions. So in a way, what I need to do is to compute the entries of the representation of this rotation as a matrix acting on the space of state. So UR is a representation of this rotation as a matrix acting on the basis of the stationary states as it was defined. And I won't go into details of the derivation, but what is important here is that even in this very simple setting where I need to find these entries of this matrix, I already find quite complicated and interesting function. So here, what you find is a product of a weight times a polynomial in blue. And this polynomial is nothing else than the bivariate generalization of the Kraft-Chuk polynomial. And the weight is the square root of the weight of the polynomial, which is only the trinomial coefficient. So if you're familiar with Kraft-Chuk polynomial, they are orthogonal with respect to the weight, which is the binomial coefficient. They are bivariate generalization. They are orthogonal with respect to the trinomial weight. And you can show this by kind of solving a recurrence relation. And something that is important to note, because we'll see that later, is that the usual orthogonal polynomial known as Kraft-Chuk polynomial, they verify three-term recurrence relation because they are orthogonal polynomial. Now, because we're considering bivariate orthogonal polynomial, we have generalization of this type of recurrence. Here, this polynomial in two variables, I and k, they will verify two different 7-term recurrence relations. So if I multiply the polynomial by I get a combination of the other polynomial in the family. And if I multiply by k, I also get a linear combination of this polynomial. The only thing that's different is are the coefficients that are highlighted in red. Okay, so again, I don't go into detail, but the idea is that even in this quite simple setting in physics, we already need these generalization of the well-known Krapchuk polynomial. If you're wondering what is the relation to the univariate case, well, if you restrict yourself to a rotation in the YZ plane, so you preserve the axis x in your initial reference frame, then the 7-term recurrence reduces to a 3-term recurrence, and this polynomial reduces to the usual Krapchuk polynomial that you'll find in the book by Kukuk, the Krapchuk polynomial as are well known in one variable. And there are also other applications, but I won't go into details of the other applications for this polynomial. The idea is that if you want in very concrete application to go to a smaller number of dimension to a higher number of dimension, you might need this generalization of univariate orthogonal polynomial. Now that I imagine we all agree that these generalizations are interesting and important, one can wonder what is the type of structure that is known and understood for the univariate Krapchuk polynomial and their generalization that we could also find and understand for the bivariate or the multivariate case. So this is a quick sketch of some of the concepts that are known to be related to the Krapchuk polynomial. In terms of algebra, these Krapchuk polynomials are known to be related to SL2. They are related to, in linear algebra, to the concept of Leonard pair. You probably know that they are associated to the adjacency matrices of the Hamming scheme. If you take a Krapchuk polynomial of the first adjacency matrix of the Hamming scheme, you get the other adjacency matrices in the scheme. And by the same way, they are related to the Hamming graph. It could be possible that, out of this structure would be very hard or impossible to generalize for the bivariate Krapchuk polynomial, but actually we already know that some of this structure translate to the bivariate case. Instead of being related to SL2, now it's related to SL3. And there's also a well-known association scheme known as the ordered Hamming scheme, which is now related to this bivariate Krapchuk polynomial. So some of the structure that we know in the univariate case, we also already know for the bivariate case, but we're still very far away from, having the complete picture that we have for the univariate case, because the Krapchuk polynomial are just one example of Askey-Wilson polynomial, which are known in general to be related to the Askey-Wilson algebra. So the bispectral algebra of the polynomial is well understood. Their connection with Leonard pair is also well understood. And each P and Q polynomial scheme are known to be associated to a polynomial from the Askey-scheme. So again, we're far away from having the same type of general understanding in the bivariate case, but the idea is that you need to start somewhere, and in this talk, really we'll consider what is the bivariate generalization of P polynomial scheme, and what is the generalization of the notion of distance regular graph. There's already some work that has suggested or investigated generalization of Leonard pair. I cite some reference at the bottom, but yeah, this will not be covered in this presentation. So let's go to the definition of multivariate P polynomial schemes, and we start with just looking at the definition of an association scheme and a P polynomial scheme. So you are probably already familiar with this, but an association scheme, you can see it as a set of matrices, A0, A1, up to AN, with certain properties. A0 is the identity matrix. If you sum over all the AI, you get the matrix of ones. We consider symmetric association schemes, so these matrices are symmetric, and the vector space they span is closed under the matrix product. So if I take AI times AJ, I get a linear combination of the matrices. These are the Bose-Messner relation, and you have some intersection number Pij,k that arise in the equation and characterize the algebra. We also know that these matrices commute and they share common eigenspaces, and you can define a basis of projector onto these eigenspaces, and these are the E0, E1 up to En, which will verify the usual relation verified by projectors. So if they sum to the identity, they are idempotent, and yeah, and they really project onto the eigenspaces of the AI. Now, a P-polynomial scheme, the idea is very simple. We just say that it's the scheme where AI is a polynomial of degree I in A1. So basically, you get all the AI by just taking some combination of monomial in A1. And so this is what this definition tells you. And it would not be very interesting if it was not related to anything else, but we know some results regarding this P-polynomial scheme. The first result is a connection between these polynomials, this P-polynomial scheme, and a constraint on the intersection number. So if you check that you have an association scheme and you look at the coefficient P1jk, and it's only non-zero when j minus k, the absolute value of j minus k is smaller than 1, and also the coefficient P1j, j plus 1 is non-zero, you know by this result that you will have a P-polynomial scheme. So basically, if a lot of your intersection numbers are 0, with respect to this condition, you know that your scheme will be polynomial and the polynomials Vi will exist. There is also a connection in terms of graph, and it's with the notion of distance regular graph. So a graph, again, I assume most of you are quite familiar with this definition, but a graph is said to be distance regular if the number of vertices z at distance I from x and at distance j from y do not depend on x and y, but only on their distance, that would be k. Okay, maybe I didn't write the definition correctly, but this is the idea. And there is a proposition here that we also have that makes a correspondence between a P-polynomial scheme and a distance regular graph. Basically, if you have a P-polynomial scheme, the first adjacency matrix A1 is the adjacency matrix of a distance regular graph. And if you have a distance regular graph, you can look at all the distance matrices, and it will give you a P-polynomial scheme. So it goes in both directions. This is a well-known story. We can illustrate everything again in an example. So if we start with the cube, which is well known to be distance regular, obviously we take A1 to be the identity because it's a condition for an association scheme. A1, we take it to be the adjacency matrix of this cube. A2, we take it to be the adjacency matrices connecting vertices at distance 2 in the graph. And you can see that it's a polynomial of degree 2 in A1. And A3, it's the matrix connecting the element at distance 3 in the graph. And it's a polynomial of degree 3 in the first matrix A1. So we have, for a univariate P-polynomial case, we have a graph interpretation of this P-polynomial scheme. We have a polynomial structure, and there's a condition on the intersection number. If you were to compute the Bose-Messner relation with A1 for such a scheme, you would find that A1 on AI only gives you AI minus 1, AI, and AI plus 1. And this is not surprising. It's a type of three-term recurrence relation, and these are known to be related by Favart's theorem to orthogonal polynomial. But yeah, the idea is that we have these three things, and in the multivariate generalization, we want to reproduce the connection between these three things. And so we can go to the definition of these multivariate generalization. And the first thing that is surprising is that now we need to introduce something that we didn't need to introduce for the univariate case, which is an order. And the reason why we didn't need that in the univariate case is that, as you'll see, that there's only a single ordering, and for if you have monomial in one variable. But and so there is a kind of monomial order which is implicit for the univariate case, but you need to choose it if you consider multivariate extension of these P-polynomial scheme. So a monomial order is just a total order on the set of monomial, such that, okay, if you have two monomial u and v, and you multiply each of them by w, if u was smaller than v, then wu is still smaller than wv. So this preserves the ordering, the multiplication by w. And it's also well ordering. So if you take a subset of monomials, there will always be a smallest element with respect in this subset with respect to this order. And just because there is a simple association between monomials and tuple of integers, basically in the rest of the talk, we use the same order for the monomial and the tuple of integers because they are in one-to-one correspondence. And so it's a bit of an abuse of notation, but this is implicit in the rest of the talk. So now that we have this notion of monomial order, we need something that will play the role of the order of the polynomial in the univariate case. So you can recall that for a P-polynomial scheme, AI is a polynomial of degree I in A1. So we need to be able to say something similar for the multivariate P-polynomial scheme. So we need the notion of multi-degree. An M-variate P-polynomial is of multi-degree n if all the monomial that appear in the polynomial are labeled by tuple a, which are smaller than n. Okay. And also you also need that the coefficient in front of the monomial labeled by n needs to be non-zero. Here n, just really note that n here is a tuple of integer, so it's the tuple n1, n2 up to n3. So this is based on the definition of the monomial ordering, and it generalized the notion of a degree of a polynomial. And here is the definition as introduced by Banai and his associate in 2023. And it goes like this. So this is the definition of an M-variate P-polynomial scheme. You have three conditions. The first one is on the domain. So basically, the way it works is that in a P-polynomial scheme, you will label all your adjacency matrices with tuple of integers. And the set of these tuple gives you the domain, so the domain D. And you need that your domain does not have any hole. So if you consider, if in your domain you have the tuple n with n1, n2 up to nm, this tuple of integers, and you choose another tuple of integer n prime, where ni prime is smaller than ni for all value of I, this n prime also needs to be in the domain. So in a way, this means that in particular, the tuple of 0 will always be in the domain. We cannot consider schemes where we don't have the tuple of 0 or we have some kind of hole inside our domain. So we cannot look at things too exotic. Also, well, the second condition is the one you would expect because it's the direct generalization of definition of P-polynomial. It says that with respect to this labeling of the adjacency matrices in the scheme, an is a polynomial of multi-degree n in the first adjacency matrices of the scheme. So the ei, they are the tuples of 0, except at the position I, where the value is 1. So these are the first adjacency matrices of the scheme, and an is just a polynomial of multi-degree n in these adjacency matrices, which kind of play the role of the variable here. And the last condition, which again is a bit surprising if you only have the univariate case in mind, is that you need to ask that if you apply AEI on, do you see the last line on the bottom? I'm wondering, yeah, okay. If you act with AEI on the monomial labeled by A, it can be expressed as a linear combination of all the monomial labeled by the tuple B, which is smaller than A plus I. And this seems a bit strange because obviously, I mean, if A plus EI is in the domain, this is free because AEI times the monomial in the adjacency matrices labeled by A will give you the monomial labeled by A plus EI. But if you go outside the domain of the scheme, because the Bose-Messner algebra is closed under matrix product, you know that it will be possible to re-express your this monomial, which is outside the domain, in terms of monomial inside the domain. And then, in a way, there is no guarantee that the B that will arise in this linear combination will be smaller than A plus EI. This is never a problem in one dimension, simply because if you look at the monomial AN plus 1 in an association scheme of degree n, you know that AN plus 1 can be rewritten in terms of all the powers of A up to n. And all these monomials are smaller than n plus 1. But when you look at a domain in higher dimension, this type of thing is not guaranteed anymore. So this is why this condition is really necessary. And yeah, and just a note, this was the definition introduced by Banai, and this third condition is very essential in the case of to have a graph interpretation. And so we went with this definition instead of the definition of bivariate scheme of type alpha and beta, where you don't have this third condition, but you have an additional partial order that you need to deal with. Okay, the idea is that this definition works better when you consider graph, and this is where we want to go. So this is the definition of multivariate P-polynomial scheme. If you have any question, feel free to interrupt at any time. And here, this proposition is the generalization of the connection between P-polynomial and the constraint on the intersection number. It tells you, if you have an association scheme, what condition you need to look at the intersection number to know that it's M-variate P-polynomial and vice versa. So if you have an M-variate P-polynomial scheme with respect to the definition of the previous slide, it means that if the coefficient P-EI BA, here the B and the A are already tuple of integers, this coefficient, if this coefficient is non-zero, it requires that B is smaller than A plus EI with respect to the monomial order that we considered for the M-variate P-polynomial scheme. And also, if you look at the coefficient PEI of A plus PEI of A and A plus EI, it must be non-zero if A plus EI is in the domain. So this gives us a characterization of M-variate P-polynomial schemes at the level of the intersection numbers. And the idea behind the proof, I don't go into the details, but basically, the first statement that a scheme is P-polynomial, it tells us that two vector space are the same. The one spun by the adjacency matrices labeled by beta, and the vector space generated by the monomial labeled by beta. So basically, the first statement tells us that these two things are equivalent. And if you want to use the first statement and prove the second, basically, you look at the second line, the action of AEI on the matrix EA, and then you can rewrite EA in terms of monomial, and then apply the equivalence of the span of the two vector space to find that the only AB that arise in this sum on the right-hand side are the B's that are smaller than A plus EI. And vice versa, if you have the second statement, you basically have the line at the bottom, and you can apply it iteratively with an induction and show that the span of the two vector space spanned by these matrices on the first line are the same, and this gives you the first statement. That's a It's a bit of a sketch of the idea of the proof, but just to give an idea of more or less how this can be proven. Okay. Okay, now that we have the definition and we know we have a characterization in terms of the intersection number, we can look at an example. So here we consider the symmetrization of a two-class association scheme. So the way that it works is you start with Z. Okay, Z is just an association scheme with two class, A1 and A2. And there is a K, B, and C are defined with respect to the intersection number of this association scheme. And from these three matrices, A0, A1, and A2, you can construct a bunch of new matrices, the Aij, and these will also form an association scheme. So the way they are constructed is by taking a sum over all the possible permutation of a certain tensor product of A1, A2, and A0. So if you want Aij, you take the tensor product I time of A1, J time of A2, and N minus I minus J of A0. And so if you do this construction and you use the relation that you know between A0, A1, and A2, because you know that they are an association scheme, you can show that the Aij are also an association scheme. You can also find some of the relation in their Bose-Messner algebra. You can show that A10 on Aij gives you this sum over AI minus 1j, Aij, AI plus 1j, AI minus 1j plus 1, and AI plus 1j minus 1. So you only have some of the terms. You don't have all the Aij that arise. And you have a similar relation for the action of A10 on Aij. And so basically, this tells you that a lot of the intersection numbers are 0. And this is, in fact, equivalent to the characterization in terms of intersection number that we had on the previous slide, that was equivalent to saying that it's Bivariate P-polynomial. So from the derivation of these two relations, we know that this symmetrization of a two-class association scheme gives us a Bivariate P-polynomial scheme. And we can also find what are the polynomials. So it's possible to show simply actually by solving. Okay, I can return to the previous slide. Here, if you rewrite Aij in terms of a polynomial of A10 and A01, this gives you two recurrence relations. And if you solve these relations, you find that this polynomial Vmn of A10, A01 needs to be again the Bivariate P-polynomial Kraftschuk polynomials. So when you evaluate these polynomials on the eigenvalues of A10 and A01, you recover the usual Bivariate Kraftschuk polynomial evaluated on I and J. So yeah, and so this illustrates the connection we had earlier. We have for this scheme, we have a characterization in terms of Bivariate polynomial, and we have also a lot of 0 intersection numbers. Also, just a note, the ordered Hamming scheme is an example of the symmetrization of a two-class association scheme. It's the case where K, B, and C take a special value. So it's a special choice of the initial association scheme Z. Okay, so now we have seen an example. We know that there is a connection between multivariate P-polynomial scheme and a constraint on the intersection number. Now we would like to complete this type of connection by looking at the graph interpretation of these schemes. And so to find the generalization of the distance regular graph that we had in the univariate case. So before jumping into the definition, we can just give a bit of intuition. So, okay, on the left side here, you have two schemes that are known to be distance regular. Well, sorry, two graphs that are known to be distance regular. These are two cycle graphs. And you have their Cartesian product on the right-hand side, and it gives you some kind of toroidal graph. So even if you start with these two distance regular graph, their Cartesian product is not distance regular. And it's easy to show this because if you take two vertices in this toroidal graph that are at distance 1, and you ask, okay, how many vertices are at some other distance I from x and another distance j from y, the answer will depend on the choice of color of the edge between x and y. So it does not only depend on the fact that x and y are at distance 1, but also on the coloring of the edges. So it's not distance regular because it depends on something else than their distance, but there is still some structure remaining, right? I mean, this graph still has some symmetry, and it does not depend exactly on the choice of x and y. It only depends on their choice, on their distance and the coloring of the edge between these. And so this is what we try to capture with this notion of m-distance regular graph. There is still some structure that exists, and we want to give an actual definition of this. So as you see, we need to define something that is related to a coloring. So the first thing we need to define is the notion of an m length. So imagine that you have a graph G, and you consider a walk psi on this graph. So it's a set of edges that are each connected to each other. And you have a partition of the edges of the graph. So gamma I is a subset of the edge in your graph, and the set of the gamma I gives you, a partition of all the edge in your graph. Then the way we define the m length of psi is basically the tuple of integers that count in the walk psi how many edges of each color you have. So the first entry tells you how many edges of color 1 you have in your walk, how many edges of color 2 you have in your walk, give you the second entry, and etc. up to m. So Lm of psi is just counting in the walk psi, how many edges of each color you encounters. Now, if we introduce furthermore a monomial order, we can define a notion of m distance. So imagine that you have two vertices in your graph, and you have this partition of the edges in some m colors. What you can do is you can consider the set of all the possible walk between x and y. And for all of these possible walk, you can compute what is the associated m length. So for each of these walk, you count the number of each color in the walk. And you can compare, this will give you a bunch of tuple of integers. And if you use a monomial order, you can compare these tuple of integers. Because it's well ordering, there is always a minimum. And what you do then is you define the m distance, not an actual distance because it will be a tuple of integers, but you define the m distance between x and y to be the smallest possible m length between x and y. The length of this, the m length of the walk with the smallest possible m length with respect to the monomial order. And so if you have your graph, you have this coloring of the edges, and you take any possible m distance, you can define, so you take a m distance L. Again, L will be a tuple of m integers. Then the way we define the m distance matrix AL of this graph will be the matrix where the entry xy is 1 if x and y are at m distance L and 0 otherwise. And then using this notion of m distance, it's defining m distance regular. It's just basically taking the definition of distance regular, and instead of using the regular distance, you use the m distance as was defined in the previous slide. So basically, a graph is said to be m distance regular if you take any vertex x and y that are at m distance c, the number of vertices z at the m distance a from x and b from y only depends on, does not depend on x and y, but only on their m distance, which is c. And from this definition, then, it's very simple to obtain a lemma, which is the analog of what is known for distance regular graph. Basically, that the m distance matrices of an m distance regular graph gives a symmetric association scheme. And the proof is exactly the same as you do for distance regular graph. You look at the entry xy of the m distance matrix AA and AB. You can split that by doing a resolution of the identity in between. And then this is just an argument of counting the number of z that verifies the condition in the definition. This gives you the definition of the intersection number, and you can rewrite this in terms of a sum of these intersection parameters times the adjacency, the m distance matrices. So again, this lemma, basically it's the same proof as distance regular, but instead of using the distance, you use the m distance. Yes, and so again, the idea is to make a connection between this graph and m-variate p-polynomial graph, sorry, an m-variate p-polynomial scheme. And this is the role of this theorem. Basically, it tells that the two statements are the same. If you have an m-distance regular graph and you look at the m-distance matrices, this will give you an m-variate p-polynomial scheme, and vice versa. If you have an m-variate p-polynomial scheme and you look at the graph with a certain coloring of its edges given by the first adjacency matrices in the scheme, the AEI, it will give you a graph which is m-distance regular with respect to this coloring. So it's, again, it's a one-to-one correspondence. Yeah. And here we have just an example, because, you know, if there was no example, it would not be interesting. So here, again, we consider association scheme obtained by symmetrization. So earlier it was a symmetrization of a 2-class. Here we consider the general symmetrization of an m-class association scheme. So here an, where n is a tuple of integers, is a sum over all the possible permutation of a1 in a tensor product n one time, a2 in the tensor product n two time, and etc. And for this scheme, we know that it's m-variate p-polynomial. And just by construction, the AEI are these matrices. So it's because EI is the tuple with 0 everywhere except a single one at the position I. If you do this construction, you find that AEI is just a sum over taking the tensor product of the identity, except at some position you get one matrix AI. And so what the previous theorem tells you is that, okay, because this scheme is m-variate p-polynomial, you know that the matrix you will get if you sum all the these AEI, which are the first adjacency matrices, it will give you the adjacency matrix of an m-distance regular graph. And in that case, if you sum all of the AEI, basically you're summing all the adjacency matrices in the original scheme Z. So you're summing A1, A2, up to AM for each entry in the sum. And what this gives you by the property that the sum of the adjacency matrices in this scheme is the matrix of 1 is that this matrix A will be more or less the adjacency matrix of the Hamming graph. So it will be a sum over the tensor product of the identity, except at one position you get the matrix J. And so what this tells you is that, okay, if you have a Hamming graph and there exists an M-class association scheme on Q vertices, then at HK of M will be M-distance regular. So there will exist a coloring of its edges such that the property of M-distance regular hold. And this is just a visualization of this for construction for a very small Hamming graph. So here you have the two coloring of the edges, and with respect to this coloring, you know that this graph will verify the m distance regular property with respect to the m distance as defined with this coloring. So, okay, this gives us the connection. And yeah, this kind of completes the picture that I wanted to present on this connection between m-variate p-polynomial scheme, m-distance regular graph, and the constraint on the intersection number. Now we can discuss a bit uniform poset, because the question that we're kind of left with is that, okay, we have this example of symmetrization of association scheme. Do we have all other examples of these multivariate p-polynomial scheme? And the answer is yes, we have many other examples. We have, you know, in the most well-known P and actually also Q-polynomial scheme, we have the Hamming, Johnson, the dual polar, and the Grassmann schemes associated to some polynomials in the Askey-scheme of orthogonal polynomials. So the Hamming are associated to the Krapchuk polynomial, the Johnson scheme associated to the dual Han, dual polar Han associated to the dual Q-Krapchuk, and the Grassmann is associated to the Q-Han polynomial. And for each of these family, we know about a bivariate p-polynomial extension. So, you know, as we've seen in the presentation, if you look at the symmetrization of association schemes, you get, of a two-class association scheme, you get a bivariate p-polynomial scheme, and the associated polynomial or the bivariate Krapchuk. But we also know that if you look at the non-binary Johnson, you get a generalization of the Johnson scheme, which is now bivariate p-polynomial. And we know the polynomial, there are some kind of a combination of dual Han and Krapchuk polynomial. It's not just a product, it's really a combination, because the variable of one is in the parameters of the other. For the dual polar, we have these isotropic subspaces, and for the Grassmann graph, we have the attenuated spaces, which are also, you know, for which the bivariate polynomials are well understood. And kind of a question is that we would like to understand is where are all these examples of bivariate p-polynomial schemes coming from? Is there combinatorial and an algebraic structure which could encompass both the bivariate and the p-polynomial scheme together and give us some kind of embedding to understand these generalizations? And to answer this question, we can turn to the uniform posets as were introduced by Terwilliger in 1990. And okay, so it's a bit late in the presentation to introduce again some definition, but okay, I'll try to be quick. So basically, uniform poset, you start to define it. You start by defining a poset. So you take a finite set X and introduce a partial ordering. And then you say that two elements are in relation that one covers the other. So Y covers X. If X is smaller than Y, but there is no Z in between, such that X is smaller than Z, and which is smaller than Y. And with this this partially ordered set, what you introduce in addition is a grading. So you organize all your vertices in this finite set, all these elements in terms of fiber, so that if Y covers X and X is in the fiber Pi, Y will be in Pi plus 1. So the only way you can be, if you're in Pi, you're only covered by element in Pi plus 1. And if you're in Pi plus 1, you're only covered by element in Pi plus 2. So it's a way of organizing the element with respect to this ordering. Yeah. And so once you have these fibers and you have this set of elements, you can introduce an incidence algebra. So basically, Li, Ri, and these Ei stars are matrices acting on the vector space where the vectors are labeled by the element in the finite set. And Li brings you from the fiber I to the fiber I minus 1. So it's a lowering operator. Ri brings you from the fiber I to I plus 1. You can see that as a raising operator in the incidence algebra. And EI star is projecting onto a fiber. And then the definition of a uniform poset, it's an algebraic definition, and it tells you that a poset is said to be uniform if the matrices Ri and Li verify this very cute relation, very simple. So you have some coefficient arising in this relation, and they need to be such that they verify certain properties. So if you organize this coefficient in a three-diagonal matrix and you look at the sum matrix, it needs to be non-singular and stuff like that. But basically, the heart of the definition of a uniform poset is the relation at the bottom. You need to have this relation between the generator of this incidence algebra. And what is interesting is that this algebra is very simple and we understand it very well. Terwilliger showed that the vector space onto which these matrices act can be decomposed in irreducible module with respect to the action of the generator in this algebra. So you can find a new basis for this vector state such that the action of the Li and the Ri and the IR stars are very simple. Again, Rj on the vector Wj will just bring you to the vector Wj plus 1. It's still very much erasing operators. There are only some coefficient arising in each module, and they are given by solving an equation. But here again, the idea is just that we have this combinatorial structure, we have this algebra, and we understand this algebra very well because we can decompose its standard module in irreducible module for which we know the structure. And the quite surprising observation that Terwilliger did in the original paper is that, well, if you are looking for this P-polynomial scheme that we were discussing earlier, you can find them at the top of each of these uniform posets. So for each of them, you can define a uniform poset so that you can embed the adjacency algebra of the scheme in the incidence algebra of the associated uniform poset. So you see this matrix A for the Hamming scheme. It's a combination of Ln and Rn minus 1 and some projection over the fiber N. N is the last fiber in the scheme. And so basically, the two elements in the Hamming scheme are adjacent if they are connected by going down by one fiber and then going back up to the same fiber on the top fiber. But they are all on the top fiber of these schemes. So the natural question to ask is, well, what happens if you look at a fiber below the top fiber? And this is the observation that we are working on right now. I mean, this is preliminary result, but it seems that if you do that and you look at fibers below, often you will find these bivariate P-polynomial schemes. So, for example, if we consider the isotropic subspace scheme, which is the bivariate generalization of the dual polar scheme, you can find its generating matrices in the adjacency algebra of the fiber I in the uniform poset based on isotropic subspaces. And the intuition one should have here is that the adjacency on the top fiber can be understood as connecting element that you can reach by going down and then going up. So there is one way of being adjacent when you're on the top fiber. But if you go on fibers below, there are two ways you can be adjacent on a given fiber. You can be adjacent by going down to the fiber below and going back up, or you can be adjacent by going up and then going down again. And so this gives you kind of the adjacency algebra associated to the incidence algebra restricted to one fiber, has then two generators, which give you the two generators of your bivariate P-polynomial scheme. So again, this is still something we're working on. The details are not all exactly clear right now, but it's just an observation that what we find very interesting and that we are working on, and that we will continue working in the future. But it already works very well for the isotropic subspace scheme, as you can see below. And this gives you like an algebraic embedding that you can use to investigate, the post-Messner algebra of these bivariate P-polynomial schemes. So I'm pretty much done. This is just a quick outlook. Basically, the heart of the presentation was relating these three things: the M-variate P-polynomial schemes as introduced by Banai, M-distance regular graph, generalization of distance regular graph, and a constraint on the intersection number of these schemes. Something that we didn't talk about is the Q-polynomial structure, but I mean, this notion of M-variate Q-polynomial has also been introduced and studied. There is just no relation between these Q-polynomial and distance regular graph, so we didn't talk about here today, but just know that this exists. The bivariate schemes of type alpha beta, where you have an additional order, we didn't discuss, but this is also interesting in many regards, but it's just, it seems to be a setting a bit different than these distance regular graph. And finally, we introduced just an observation regarding these bivariate P and Q-polynomial scheme and what lies below the top fiber of uniform poset. Yeah, and if any of you are interested, here are some reference on these different things. If you want the definition of multivariate P and Q-polynomial scheme, it's the second reference by Banai, 2023. M-distance regular graph, it's the third reference. And I also recommend highly the paper of Paul on uniform poset, the incidence algebra of uniform poset. I found it really interesting. So I think it's the best reference on this. And also, yeah, there's also examples, many papers on special case of M-variate P and Q polynomial schemes. These are listed below. And yeah, thank you all for your time.
Thank you for the nice talk, Pierre. Any questions?
I have one question.
Yes, please.
Okay, thank you, Pierre, for a beautiful talk. So I'm interested in this M distance regular graphs. Is there any combinatorial structure of a graph? Do you have any results regarding combinatorial structure of a graph? In particular, I will be happy if you have something about equitable partitions.
No, we really like, we don't really have much right now. I mean, if you have like a structure, so that you are interested in particular, I mean, feel free to write, and then I can by myself take the time to think about it. But for now, I mean, maybe Xiang has a better idea because she also she also is quite familiar with this. But for now, we really like made the connection with these schemes, but we didn't investigate much, question that are more coming from graph theory. So I mean, I would be very, very interested if you have any idea, and you could write to me by email. But yeah, for now we don't have really much to complete this story. But I believe there's probably a lot interesting thing that can be looked into. Yeah.
Okay, thank you.
Any other questions?
I have a question, if I may.
Okay.
Pierre Antoine, on one slide, early slide, you mentioned perfect state transfer. Can you make maybe more comments on that topic related to the what you've talked about? Thanks.
Yeah. Yeah. Okay. So maybe the simplest thing I can say on the ordered Hamming scheme, they are known to be both perfect state transfer and fractional revival. Luc did a paper on that with Mickey, I think. So basically the idea is that, well, this multivariate Kraftwerk polynomial, they also have well-spaced spectrum. So the eigenvalues are also labeled by integers, and so you can work you can work it out so that you have perfect state transfer. So yeah, that's pretty much all I think I can say on this. But yeah, if you want the graph, the Hamming scheme gives you an association scheme, a graph with a equally spaced spectrum in one dimension, and then these generalization give you the same spacing but in higher dimension. So that's why it would be yeah. That's why I believe it's interesting here.
Thanks.